can record. So you are welcome once again. So I said this week we'll be talking on. Can you see the screen back? I've returned it back. Can you see it? Can you see it? Hello? I always want
Yes,
to
sir.
express. If you are not seeing it, let me know. So I said today we're talking about
Yes, I can see it.
the first law of thermodynamics. So I said intended learning outcomes. At the end of this lesson, students should be able to write expression for work for different systems, explain heat transfer into or out of a system. So mentioning system now should not be a new thing because we've been able to define terms. We've talked about systems, surroundings, and different types of system. And I explained heat transfer. If it is transferred into a system, it is denoted by a positive sign, while if it is lost to the surroundings, it is negative. Also, at the end of this lesson, you should be able to state the first law of thermodynamics and write modified equation of the first law under different known process. So let's begin with work. I hope you always jot this thing down, although they are in your materials, but it helps you to learn more. So let's look at work. Here, we look in some details at how energy can be transferred as heat and work between a system and its environment. Now, we said, let us take our system as a gas confined to a cylinder with a movable piston. The upward force on the piston due to the pressure of the confined gas is equal to the weight of the lead shot loaded on top of the piston. So if the piston moves up, that equals to the weight of that lead shot, as it is clearly stated there. So the walls of the cylinders are made of insulating material that does not allow any transfer of heat and or heat as a form of energy. Now, looking at this, you can see the cylinder there. Now, it has been compressed. But if the piston moves upward, we are talking about compression. We talk about compression of a gas confined in a cylinder. Now, let's assume the piston moves upward. That is the piston. The movement of the piston upward equals to the weight of the lead shot that gave us the pressure applied. So this bottom of the cylinder rests on a reservoir for thermal energy. And a thermal reservoir, probably a hot plate, whose temperature T you can control by turning up. You have some what's it called? A hot plate that can control the temperature, can increase it or decrease it. Now, listen to this now. So the work done, that's change in work done, the system in the process described above equals to D change in W equals to P A dx. Do you understand that? Hello? Can you hear me? Hello? Can you hear me? Hello?
Yes,
I
can hear you,
want
sir.
to be sure that you are still connected. Probably are not disconnected.
Yes, sir.
I would like to call your attention. Now, so we are trying to describe work done here as a product of the change in work done, a product of the pressure and the area. Now, we are saying A dx equals to dV. So the whole of this A dx here is replaced by what? dV. That area is like the integration of area will give you volume. A good student of mathematics, of integration, should know that if you integrate area, you get volume. If you differentiate volume, you get area. If you differentiate area, you get what? Probably the length or the breadth, as the case may be here. So the ADX there gave us the V. So dW, change in work done, equals to pressure multiplied by change in volume. But note something there. There's a negative sign there. Negative sign is telling you that there's what? A decrease in volume due to the application of what? Pressure. If there's pressure, there will be a decrease in volume. According to which of these laws? Is it Charles' law or Boyle's law? P1, P is inversely proportional to V. That's why you have P1 V1 equals to P2 V2. Can you remember that? Can you remember that? Can you remember that? Can you remember that? Hello? I want response.
Yes, sir.
Okay. Ebenezer, you can unmute. If you don't have a noisy background, you can unmute so that by the time I want response from you, you can respond on time. Because of time, it's still about 10 slides to check. Now, we have been able to summarize the work done in the system by a complex external force. You know, the external force here that we're describing here is from the lead shaft that decreased the volume, that applied the pressure. So we're looking at different systems here. We're talking about wire. The tension there is a form of force. The displacement is the L. So the work done is force times change in what? Change in length. So also we look at a film. A film, the force there is surface tension. So and the displacement is what? Area. So surface tension multiplied by the area. Now, and if you are to define work done, what is work done? What is work done? You know, in our
work done is a DS.
What is work done? If you are told to get work done in your conventional, the normal work done, the definition you have. Work done is a product of the force times this distance covered. So that's why you have the representative of the force and the representative of the distance or the displacement, as the case may be. So these are different systems. You have your wire, you have your film, you have your fluid. That's why you have pressure, PdV. The one we were talking about before was a volume. We're describing pressure applied to a volume. The magnetic field multiplied by what? The magnetization. So the dielectric system, it is electric field multiplied by what? The polarization. Simply force times distance. And distance is a scalar quantity, so we can use displacement so that it has a direction. So it is force multiplied by displacement. I guess you get that. So this table is very, very, very important. Now, work done, it is a form of it is the integral of change in work done is given as what? PdV. So if you integrate this well and insert the value, it will give you the actual work done. And I said there that note that if work done on a system, if work is done on a system, it will be positive work. And if work is done by a system, it is a negative, it will be negative. Can you see the difference? If work is done on a system, it's as if someone is serving you plate, you are not consuming your energy now. So it is positive work. And if work is done by a system, if you do work, that means you will expend some energy. That is why it is negative. Do you get the analogy now? I guess you get that because of time. Let me just proceed. I said, now, it's another survey now. I said, work in a quasi-static process. For a quasi-static isothermal expansion of compression of an ideal gas, the work done is given as that. Now, the question is, what is the meaning of quasi-static? Can anybody tell me the meaning of quasi-static? Because we can't just be using terms without knowing the meaning. What is the meaning of quasi-static? Anybody? Anybody? It is a process that is not reversible. Is that clear? Did you get that?
Yes, sir.
Or we say happening slowly, or it applies to be what? To be static. That's what the dictionary states it. So for a quasi-static isothermal is what? That means it is independent of what? Expansion of compression or compression of an ideal gas is given as that equation. But for an ideal gas, in which the equation of state equals to PV equals to nRT, where N, you know this ideal gas equation, right? Hello? Hello? I guess you are familiar with this, what's it called? The ideal gas equation, PV equals to nRT. There are equations you must have come across during your secondary school days. Now, we said PV equals to nRT. So we are making P the sort of formula. We now have nRT over V. Now we now replace the value of P with this new derivation from the first equation, from this first equation. We're trying to derive work in a quasi-static process. Remember, that's what we're trying to do. So if you replace V, so it will now be nRT over V dV. Now, nR and T are constant. Now, if you look at that, so you'll be left with 1 over V dV or dV over V. And if you are a good student of mathematics, if you have an expression like that, it will give you natural logarithm of V. And you now apply the integral from final to initial. So these are just simple mathematics. So if you have the A over A, so what it will give is this to be ln A, then the infimum and the supremum of the integral. A good student mathematics should know the upper limit and the lower limit. Those are what we call the infimum and the supremum. So basically, you just apply that. So you apply the upper and lower band into this equation and you get an actual value. So we have not done any magic here. What we did there was we started with this work is product of force applied and the displacement. Now we now say P in an ideal gas equation, PV equals to nRT, making P the formula which is nRT over V. So we substitute into this equation, and since the function the nRT are independent of the derivative V, so we brought it out as a constant. So we have the V right now. We got this now. So this is the work done in a quasi-static process. So the work done is minus nRT, natural logarithm of V final divided by V initial, and V is volume, final volume over what? Initial volume. Now, let's look at another relation. So if you're told to define work in a quasi-static process, you should be able to derive this. You're just going to relate an ideal gas situation into the equation. So let's look at the relationship between work and internal energy. I said when an adiabatic work, so at DW, at the AD represents adiabatic, is done on or by the system. I'll be able to explain that if work is done on the system, positive. If work is done by the system, negative. The internal energy of the system changes. The change in internal energy, that is change, that's delta U, don't mind me using D here, is equal to the adiabatic work done. Get that clearly. They said if when an adiabatic work is done on a system, the internal energy of the system changes. So we're not saying that the change in internal energy is equal to the what? Adiabatic work done. And you know we've defined all this before: adiabatic, isochoric, I think there are about 2 or 3 isobar and the likes. So the change in work the change in work done by an adiabatic process is equals to what? Change in the internal energy. We're just trying to relate internal energy with work done. Hope you are getting that. So let me repeat that again. I said when an adiabatic work is done on or by the system, the internal energy of the system change. When adiabatic work is done on a system, its internal energy is changed. So this change that we are talking about is now equals to the what? The change in the internal energy is now equals to the adiabatic work done. So the internal energy probably lost or gained is equals to the work done. So it is nothing is missing. So if you are saying there's a change in internal energy of a system, it is as a result of the work done. So that if 5% of it is changes or is lost, because here you have work is done on a system or by the system. So if like, let's say you have something like, let's use 10, and due to change in internal energy, it reduces to what? 8. That means the change in internal energy is +2 or -2 as the case may be. And we're not saying that change in internal energy is equals to the what? Adiabatic work done. Now, say if a system changes from state 1 to state 2 by doing adiabatic work, and if the states are different by finite amount, then the work done is equals to what? Work done in 2 minus work done in 1, which is equals to what? The adiabatic change in adiabatic work done. So it's just the same thing. We're just trying to buttress what I've said, and I see the same du equals to the w, which is the adiabatic or change in adiabatic work done. Now, looking at the next point, there's suppose the work done is mechanical work. Then change in internal energy will be a product of the pressure and a change in volume. Is that clear? Hello? Are you still connected? And about 4 of you still there. Can you hear me?
Yes, sir. Yes, sir.
Good. Now, so that is, so if it is mechanical, it will be the change in internal energy will be product of the pressure and the change in volume. But for others, it will be equal to the change in the adiabatic work done. Is that clear? Please note this. It is very, very important. Now let's go to it. I think I've talked about heat before. I said heat is a form of energy that is transferred from one part of a system to another, or to another system by virtue of temperature difference. We have talked about that over time. If you are holding a very hot pot, the only reason you are feeling it is the fact that it has been transferred from the hot pot to your hand. So you feel it is hot. The same thing is if you are holding an ice block, you discover that it is cold. It's because the temperature of your hand is much more higher than the temperature of the ice block, as the case may be. So we say that, as earlier discussed in previous class, temperature gradient determines the direction of heat flow, which I've said that. When it flows in or out of a system from its surroundings, it can flow in from its surroundings or from the system to the, listen, let me state that again. It can flow from a system to a surroundings, and the vice versa can also happen from a surrounding to a system. So the temperature of the system increases or decreases. Definitely, if you put if you boil water, for example, now the temperature increases. Is that not so? But that means it is gained from the surroundings. But if you leave it after a while, the temperature drops. So it is lost to the surrounding. So we're not trying to relate it with internal energy. So we're not saying that the internal energy of the system changes from its initial state to the final state. So the internal energy of a system must be equal to what? To the heat flow. So the change in internal energy must be equal to what? The heat flow. Now, if it's the final heat, if you subtract the final heat from the initial heat, and you're getting a negative sign, that means heat flows from the system to the surrounding. And I've said that over time. If the final temperature, subtracting from the initial temperature, and you're getting a negative value, that means it flows from the system to the surrounding. Just like, and an example of that is when you have boiled water and you leave it for some time, it is flowing, the final temperature, let's say, is 100 degrees centigrade. Is that also 100 minus what? Let's say minus 90. That's 10. That means the Q there is what? Positive. That means when Q is positive, then there's a flow of heat into the system. That means the system has gained heat. But when Q is negative, the system has lost heat from the system to the surroundings. I have less than 10 minutes. Hello, showing color report. What are you trying to say? You can unmute. Showing color.
Okay, sir. I am not fully clear about that very point.
No.
I'm not fully clear about that point. You
Okay.
said if there is a heat transfer from a system to the surroundings, that
No.
is
Okay.
that is negative.
Yes.
Okay, so if there is a heat transfer from the surroundings into the system, that is positive.
If there is a heat transfer from the surrounding to the system, that is positive. If it takes in heat,
okay,
it's positive.
Okay.
If it loses heat, it is negative.
It's negative.
It's like you are giving food on your bed. Exactly. You're not losing anything. But if you are told to jog a kilometer, you are losing something. So it is negative. Do you get that? Okay, so let's proceed. We have less than 8 minutes. To the next slide. So I said it's bat or it reservoir. This is a body that is so large. We have described that in the first slide. That is so large that its temperature does not change appreciably when it flows in or out of a system, it is kind of, it's its chamber. It keeps it, so it does not really flow in or out of system, or in or out of it. So we're trying to talk about its reservoir, its sink, just like
Okay, sir. Thank you, sir.
Okay. Just like its bath, this is a body that is so large that its temperature does not change appreciably when it flows in or out of it. Now, we notice that the temperature of its sink is lower than that of its bath. So if you want to work with something small, you can use a heat sink. But if you are looking for something large, you use a heat bath. Let me quickly go to the first law of thermodynamics. From our discussions, we have learned that the internal energy of a system can change only if there's flow of heat into the system or out of the system. And also two, work is done on the system or by the system. We have mentioned that too over time. Hence, the change in internal energy of a system is given by this, which is Q minus W, where Q is the heat and W is the work. So this is the simple, what's it called? Expression for the first law of thermodynamics. So the differential form is du equals to dq minus W. So change in internal energy is equals to change in quantity of heat minus work done. So the statement of first law of thermodynamics states is the internal energy of a system. Hello, can you hear me? So the statement of first law of thermodynamics is the internal energy of a system tend to increase if energy is added as its Q, and tends to decrease if energy is lost as work. If energy, if energy is lost, hello? 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 I want you to unmute now. We're about to round off. So if you are told to state the law of first law of thermodynamics, if you just write change in U equals to dq minus P dV. Now, the statement of first law of thermodynamics is that the internal energy of a system tend to increase. We're talking about this. The internal energy of a system tend to. Sorry, I don't know why that had to cut me off. Okay. Can you see the slide now? Can you see the slide now? Please respond.
Yes, you can see the slides.
Okay. Let me continue. If it cuts me off, please rejoin the class so that you can round off. So if by chance there's something log you off, click on the link again and join. So I said that the statement of first law of thermodynamics is that the internal energy of a system tend to increase if energy is added as heat, which is denoted by Q, and tend to decrease if energy is lost as work by the system. So who can now give me a proper definition of the first law of thermodynamics? Who can give me that? So what is the first law of thermodynamics? It states that energy can neither be created nor destroyed, but can be transformed from one form to the other. Is that not so?
Yes, sir.
That is what you know. So now, this is an expression of that. So the internal energy cannot be lost, but it can be transformed as heat lost or in form of work done. We'll be able to relate work done and internal energy. We'll be able to relate work done and heat. So that proves the fact that energy can neither be created, but can be what? Can be what?
Can be transformed from one form to another.
Yes, can never be created. So it can be transformed. The loss in internal energy may be due to the work done, or maybe due to loss or gain in temperature, but it is definitely transformed from one form to the other. So if you're not to write an expression in that light, it will not be du equals to dq minus p dv. Now, I guess this should be the last slide. So I said you should read up these three. Please, can you quickly screenshot this? It's inside your course material. Do you have it already? I said you should read up force constant, thermal response, and read up special cases of first law of thermodynamics. I think that's clear enough. Hello?
Thank you, sir.
So I guess, okay. So you read this up. Let me see if I can still share the material. But if we are logged out, we can just end it like that. But let me see if I can bring up the course material. But in case it goes off, it will meet till next week, Thursday. Thank you. So what we have done so far is for you to go back.